Hello, Mr. Burrell here. We're starting right off with Unit 8. We're talking about exponential and logarithmic functions. Specifically in this unit, we're talking about graphing exponential and logarithmic functions. You probably don't know what logarithmic functions are, and that's okay. We're going to start real basic. We're going to start talking about exponential functions, what exponential functions are, what an exponent is, some of the rules we already know about exponents, and extend that to some of the more difficult things that we're going to be doing this unit. So one thing I want to bring up first, I really like this visual. So I had a starter in class where I asked, would you rather have $10,000 right now, right off the bat, no questions asked, or would you rather have 2 pennies on the first square of this chessboard, 4 pennies on the second square of this chessboard, 8 pennies on the third square of this chessboard, 16, 32, etc., etc., etc. Would you rather have $10,000 or that many pennies, the number of pennies that are on this entire chessboard? And at first glance, this doesn't seem like a whole lot of money. I don't want pennies, I want 10 grand. Boom, in my pocket, love it. But you start to notice as this continues to increase, it continues to double every time, you notice that it just keeps getting bigger and bigger, faster and faster. That number gets big really, really fast. And you notice that on the last square of this chessboard, the number of pennies that you have is 2 to the power of 64, because there are 64 squares on this chessboard. This was 2 to the 1 pennies. This was 2 squared pennies, 4, 2 to the third, 8, 2 to the fourth, 16, etc., etc. So on the last square of this chessboard, I had 2 to the 64th pennies. To put that into perspective, 2 to the 64 power is like 1.8 times 10 to the 19th power. That's like in the quadrillions. Quadrillions of pennies. Can you even imagine? The reason I bring this example is because this is an example of an exponential equation. If I wanted to figure out how many pennies I had on the 64th square of this chessboard, I'd plug 64 into this equation, the equation 2 to the x. This is an exponential function. So that's what we're going to start talking about. We're going to start talking about exponents, exponential functions, why they're important, where we use them, etc., etc. So by the end of this lesson, I hope that you're able to know that exponential functions increase faster than linear or quadratic functions and know the properties of exponents. So you might remember some of these rules associated with exponents. The product rule, the quotient rule, the power rule, negative rule, etc., etc., etc. Let me move this down so you can see the bottom one a little bit better. There's all these rules associated with exponents that we follow in order to simplify exponent expressions. And this is something that we've learned it before. We learned about it in past math classes, but it's important, I think, to get this type of information down pat, because we're going to be using it a lot in the upcoming concepts in the upcoming units, so it's going to be really helpful to have this in our back pocket. For example, x squared times x to the third is x to the 5th. I add these exponents. P to the 5th over p to the 1st is p to the 4th. I subtract these exponents. M to the 4th to the 6th is m to the 24th. I multiply those exponents. F to the negative 9 is really 1 over f to the positive 9. It switches places in that fraction. Xy to the 3rd is really x to the 3rd, y to the 3rd. This cubed, this exponent of 3 distributes to each of those terms. B over c to the 7th power is really b to the 7th over c to the 7th. This exponent of 7 distributes to both of these terms. K to the 0 power is 1. Anything to the 0 power is 1. And p to the 1st power is just p. Anything to the 1st power is itself. So if you need to review those, now is a good time to do so, because lots of these things that I just expressed we're going to be using a bit of in the upcoming lessons. Okay, there are some questions that I want to answer. Jeez, sorry. And I want to bring up a graph in order to do so. Let me get out of here real quick. So I have listed here, let's see, where did it go? I have listed here a bunch of different functions. Let me open this one real quick. This one specifically way. Okay. So, I have 4 different functions. Y equals 2x, y equals 2x squared, y equals 3x cubed plus 2x squared minus 8x plus 5, and y equals 2 to the x power. So notice what each of these functions looks like. Y equals 2x, that's just a straight line. It increases at the same rate forever and ever and ever and ever. Y equals 2x squared, that's a quadratic expression, so that's going to be a parabola, this big U, so it kind of goes out like this. This expression right here, 3x cubed plus 2x squared minus 8x plus 5, that's this green one right here. That's a cubic function. It kind of goes on this rising roller coaster type situation. And then this last one is an exponential function, y equals 2 to the x power. Notice how fast it increases. It starts off really low and it just starts to skyrocket. So some of the questions that we were asking is which graph has the greatest y value at x equals 5? Which graph has the greatest y value at x equals 10? Which graph has the greatest y value at x equals 15? And which graph is increasing the fastest? So if you look here, at x equals 5, so like right about 2, 4, so right in here, the value that has the graph, that has the greatest y value is this green one, the x cubed function. At x equals 10, the graph that has the highest y value is still the green one, this cubed function. But you notice they're starting to get a lot closer together. So when x is equal to 15, if I come all the way up here, I have to go and go and go and go and go and go and go. The one that's going to have the highest y value is indeed the exponential function. Because when x was equal to 15, this green function, it only went to like, I don't know, right here-ish. So this exponential function got big really fast. It got really big really fast. So when we're talking about exponential functions, that's one of the qualities, one of the really cool things about exponential functions is they increase really fast. We saw that with the chessboard, with the pennies. 2 to the 64th power got really big, really fast. So that's kind of what we're talking about when we're talking about exponential functions. We're talking about these functions with a pretty specific characteristic that they increase exponentially fast. Have you heard this? Like, that was exponential. Maybe you haven't. Maybe that's not a cool term. But exponential functions increase extremely quickly. Right here, some things to know. An exponential function is a function of the form f of x equals b to the x, where the base b is a positive constant other than 1, and the exponent x is a variable. Right there, this characteristic right here, that the exponent is a variable, that's what makes it an exponential function. Exponential functions are characterized by having the variable in the exponent. Again, that's what makes an exponential function. Notice that there is no single parent exponential function because each choice of the base b determines a different function. So let me show you an example of that real quickly here. So if I go back in here, let me find my exponential functions. Okay, so for example, this function is y equals 2 to the x power. That was the function that modeled our chessboard situation. This function is y equals 3 to the x power. It's increasing even faster. Y equals 4 to the x power. Y equals 5 to the x power. They keep increasing faster and faster. Y equals 12 to the x power. Y equals 100 to the x power. Look how fast those y values increase as I change the base of this exponential function. So again, that's one of the really cool things about exponential functions. So, you might be asking, Mr. Burrell, who cares? Why do I need to know this? Well, here I want to show you some of the examples of where you see exponential functions in the real world. For example, people that use models to model population growth or radioactive decay. If you go into something like statistics, or if you go into something like physics or chemistry or things like that, you talk a lot about exponential growth or exponential decay of radioactive materials, of other sorts of materials. And these aren't all of the examples, but one of the more specific examples that is really applicable when we talk about exponential functions is when we talk about interest rates on a loan or on like a mortgage or on an investment account. An exponential function can be used to model how much money you can make after a given amount of time on a investment account. So for example, I have looked up this calculator. This is a calculator that's been programmed. It's on the internet. You can find it. That tells you, given how much money you start with and what interest rate you have, how much money you can make in an investment account after a certain amount of time. And this function that I showed you right here is the function that's programmed into the computer, this exponential function, to calculate the amount of money that you'll have if you invest after a certain amount of time. So for example, right here. So say I start with $1,000 and I add an extra $100 every single year to add to this investment account. And I want to let it grow for 30 years with a 10% interest rate. I'm going to kind of just throw in numbers in here. So the amount of money that I'll have at the end of those 30 years is $35,000, $35,543. Not too shabby. So what if I start with $5,000 and I invest an extra $600 every year for 30 years at a 10% interest rate? Look how fast this number grew. $195,813. That's a lot of money. And it grows really fast. And the reason that is because what banks and loan officers and people, the system that they use, the function that they use to calculate the interest that you make is an exponential function. So those are some of the things that I wanted to bring up to help you understand. This is just kind of an intro. Some of these are really basic. But exponential functions have a lot of power, and I think they're really cool to talk about. That's why we talk about them. Hopefully by the end of this lesson, you now know that exponential functions increase faster than linear or quadratic functions. And hopefully you know some of the properties that we use in association with simplifying exponential expressions. So I hope that was helpful, and I hope that you enjoyed that as much as I did.